right, so Kirchoff's laws. Kirchoff's laws, they don't necessarily help, well, they do help you solve a problem, but really what they do is they're great like informational tools. Last class we talked about how we can solve more complex circuits, right? If you have like resistors that are in series and parallel, how do you find the total resistance and then the voltage and current through each one? And it was pretty simple, right? We just need to remember the characteristics of each circuit and we can figure out what's what. Kirchoff's laws, you know, it's pretty good. I'm sorry, before we get to Kirchoff's laws, if we just have a circuit like this, right, we could do this the way we solve the other problems, right? We don't need anything special. We can just remember that, all right, the total resistance is going to add here. You know, we're going to do these for parallel, and then this whole thing is going to be in series with this one, and we can go through, break it up, put it back together, things like that, okay? Now, it gets more difficult. It gets more difficult, though, when you get something like this. What happens if you got something where you've got like two power sources, right? What if you've got two batteries in there? There's another chair over there, right? If we've got two batteries, we can't necessarily use the information that we used previously, right? It's still useful to us, but we don't have any sort of information that's going to say, all right, we've got two battery sources. Here are the characteristics. This is what we can do with it. Okay? This is now where Kirchoff's laws can come in. Okay? So again, here was just basic circuit stuff. Here you need Kirchoff. Right, that's where you need Kirchoff there. So that's a really good tip. If you are looking at, if you get a problem and you see a battery that has multiple, you see a circuit that has multiple batteries in it, Kirchoff's laws right away. Just go right to Kirchoff. Okay. How do I, does it allow me to extend the page? Probably not. Okay. We're good here? We're good? All right. I guess it doesn't like that. Okay. So there's two rules when it comes to Kirchoff's rules, all right? First, there is the junction rule. Sometimes you'll see it referred to as rule number 1. Okay? And all it says is that the sum of the current entering a junction must equal the sum of the current leaving a junction. I'm sorry, this pen is just gross. I wish I had a better answer for you, but it just doesn't write very well. So what we're saying is that if we have some sort of current, let's say we have a junction right here. So imagine this was just like one piece of a parallel circuit. Okay, it's just a little bit of a parallel circuit. What Kirchoff's law is saying, or the junction rule number 1, right, of Kirchoff's law says that if we have current going in here, right, when it hits the junction, some is going to go this way, some is going to go that way. Okay? And when we write that in equation form, we can say that I1 has to equal I2 plus I3. Okay? Now, the important thing about this is that, and something to keep in mind, is that it doesn't matter what direction you pick the current to go in. Okay? The important thing is that you just keep that convention. The worst thing that can happen is you'll get the incorrect direction, but you'll get the correct magnitude. Right? So if you pick the current to be in the wrong direction, but by looking at this, let's say you have I2 going this way, and then I3 goes that way, I1 goes that way, you'll just get a negative current. So it just means it's going the opposite direction of what you picked to be the positive direction. Does that make sense? Okay? So there's no detriment, there's no bad thing, there's no penalty for choosing the wrong direction for it to move. Not a big deal. Okay? Okay. So this was a question on the AP test last year. It was either on the AP test or it was on the practice AP test that we gave last year. Rule number 1, okay? Rule number 1 is an application of the conservation of charge, of the law of conservation of charge. And if you think about it, it really makes sense, and it's pretty simple. All the charge that we have going in there needs to be equal to all the charge that splits off into those other two paths, right? Charge can't just disappear. It's not like, sweet, we're at a junction, I'm out, right? Got to go somewhere, okay? So again, rule number 1, the junction rule, is just conservation of charge. Can't lose it, we can't gain it. It has to go somewhere. All right? Pretty simple? Pretty simple. All right. So the next rule is called the loop rule. Not the lop rule. Come on. So in the loop rule, what the loop rule is telling us, or says, is that the sum of changes in the potential difference, in the potential, I should say, which means we're talking about voltage, okay? For any closed loop must equal 0. Okay. So when we have changes in the voltage, right? So that means, remember the diagram, the GIFs that we looked at. Change in the voltage would be battery source, right? Battery source going in there. Okay, that would create a change in voltage. Whenever there's a resistance, a resistor, a light bulb, whatever introduced in there, that used some voltage, right? Because we saw it lower, right? The sum of them, and the loop needs to be closed, the sum of them needs to equal 0. Okay? Someone asked, does it have to go back to 0? This is why. Okay? So if we look at that from something like this, right, where this is V, we'll call this just R1 and R2. What we can do with this is, first we can, and we're going to do a couple problems, but what we want to do is we want to pick a direction that the current's going to flow in, okay? And we'll just draw it on there. So I'm going to say that this is the direction I'm going to go around the circuit in. Okay? So using the loop rule, I can come up with some information. So if I start at the battery, what side of the battery is this? Positive, right? So we're going to say it's going to add voltage. Okay? So because it's adding voltage, we're going to call it V, right? Just positive V, I should say. If we took the battery and we flipped it, right? And we took this to be the direction, then we would call it negative V. Okay? Now this guy is going to use some of that voltage, right? Okay? What is voltage? How would I write this if I want to in terms of R, but I need to talk about voltages? What should I use? IR, right? Ohm's law, right? I want to talk about in terms of voltages, but I need that resistance stuff in there. Okay? So in this case, oops, sorry, I don't want the. Because it's using it, I'm going to call it IR1. Right? Does that make sense? Okay. Now, the reason why I'm calling it I is because, remember, in a series circuit, everybody gets the same current. If we were talking about parallel, we'd need to give them like I2, I3, I1. They'd all get different names. All right? And we'll see that in a problem as it comes up. Now, if we follow this, we get positive V minus IR1. And again here now, minus IR2. And at that point, it comes all the way back, and we're down to 0, right? So that needs to be equal to 0. Okay? So to put it just a little more simply, we could say that the voltage that we used is equal to I R1 plus R2. Right? So the voltage supplied is equal to the amount that each of the resistors used. Okay? Sometimes this helps us solve problems. A lot of the time it gives us more information to work with. A lot of times you'll get a problem where you have like 3 unknowns in a circuit, and you're like, well, if I have 3 unknowns, that means I need 3 equations. V equals IR can only get me so far. The loop rule and the junction rule will help us get there. Okay? So just the same way that the junction rule was an application of a conservation of charge, this is an application of, what do you think? If we're talking about voltages, if we're talking about potential voltages, what do you think it's an application of? There's no such thing as conservation of voltage. What is conservation, what is voltage talking about? Energy, right? So the loop rule is an application of conservation of energy. So remember, potential is that work that needs to be done to move the charge from one place to another. Okay? And when we talk potential, we mean voltage. All right? So yeah, so the loop rule is an application of conservation of energy. I have really poor handwriting usually, but this is even worse on this board. Okay? Did we get all of it up there? Everybody's good there? Okay. All right. So now let's see, how do we use them? How do we apply Kirchoff's laws? Right? Okay. So there's just a couple things that we need to do when we do this. The first one is for the junction rule. What we want to do is, first thing is label the currents. And then pick a direction for them to flow. Okay? And it'll make sense. We're going to do a problem where we'll come up with some information from it. Okay? For the loop rule, what we're going to do is identify a closed loop. Identify. And then pick a direction. Wow. to go around. Yeah, I'll just pick a direction to go around, right? Okay.